Hello, I just wanted to go over the lab on conservation of linear momentum with you. The lab this week is focused on conservation of momentum, and most of the time when we deal with this principle of conservation of momentum, it involves collisions of some sort, whether it's two cars colliding together, two ice skaters maybe pushing off from one another, or billiard balls colliding and bouncing off. We're going to apply that principle to think about how the objects move after they collide. So this lab is going to help you learn about that a little bit more in depth. So let me share my screen. I'm going to go to the Blackboard site for our course, and we're going to go to the laboratory. And we are on Laboratory 5, which is Conservation of Linear Momentum. Here's the link for the simulation. Click that. And then you're going to click on Explore in one dimension. We're only going to do collisions in one dimension for this class. So here you're going to see two objects, and these are the two objects that are going to be colliding, and you're going to be analyzing the momentum of these objects before and after the collision. Let me stop sharing, and then I'm also going to bring up the lab manual for this. Okay, so here's our lab manual. There's two types of collisions that we're going to be focused on. The first type of collision we're going to look at in this simulation are collisions which are called elastic collisions. And these are the kinds of collisions where the objects bounce off of each other. The best example of an elastic collision are billiard balls. When they collide, they hit, and then they bounce off. And in elastic collisions, the momentum before the objects collide, the total momentum of the two objects before they collide, is equal to the momentum of the two objects after they collide. So that's what conservation of momentum means. The total momentum of these two things before they collide is equal to the total momentum of the two things after they collide. And another unique thing about elastic collisions is that energy is also conserved. So the kinetic energy of the system, the two objects, before they collide is the same after. There's no energy loss, right? All of the energy goes into the collision. They bounce off of each other. And that energy, it's almost like a spring. They collide, the spring compresses, and then that spring completely pushes them apart again, and the energy is conserved there. So let's try one type of elastic collision. So I have the mass for object 1 is going to be 2 kilograms. The mass for object 2 is going to be also 2 kilograms. So two objects of equal mass colliding. The first mass is going to be moving in 1.5 meters per second, and the second mass is going to be going negative 2 meters per second. The negative is just telling us that it's going in the opposite direction as the other one. So let's calculate the initial momentum of the system before they collide. Momentum is equal to, as you can see up here, mass times velocity. So let's find the momentum for the first mass. It's going to be the mass, which is 2 kilograms, multiplied by its velocity before the collision, which is 1.5 meters per second. So that's going to be 3. The units for momentum, since it's a mass times it's a velocity, the units are kilogram meters per second. I won't write that here, but that's the units. The other object has a momentum of 2 kilograms multiplied by negative 2 meters per second. And that's going to give me negative 4. So the total momentum of both of these objects before they collide, you just add up the momentum of each one individually. So 3 plus negative 4, that's going to give me negative 1 kilogram meter per second. That's the initial momentum of the system before they collide. After they collide, it should be the same, negative 1. Okay. So let's run the simulation and see what happens. We're going to run the simulation and we're going to figure out what is the velocity of each one after they collide and calculate the total momentum after they collide. So let's do that. When you get into the simulation, again, explore one dimension. You're going to click on more data. And then you're going to change the masses of each one. You both want them to be 2 kilograms. So type in 2 for that one. Click here, type in 2 for that one. So they have the same mass. And we're going to make the velocity for the first one 1.5. And the velocity for the second one was -2. So just click negative right here to make it negative and then 2. Okay. I'm going to make this slow so we can see what happens. Okay. So let's see. They collide and bounce off of each other. Notice that the little table down here is now showing that mass 1, its velocity is now -2, right? It was moving to the right at 1.5 meters per second. It collided with mass 2, and now it bounced and it's going the other way. So its velocity changed directions, and its velocity is now -2. Mass 2, again, it collided with mass 1, and it was going -2 meters per second before, and then it bounced off, and now it's going positive 1.5 meters per second. And it calculates the momentum here for you. So you can just type that in. See, it's just 2 kilograms multiplied by -2. So that's after the collision, mass 1 has -4 momentum, and mass 2 has 3 kilogram meters per second of momentum. So let's go back into the simulation and type these values in. Sorry, let's go back into the lab and type these in. So the velocity for the first one is now -2. The velocity for the second one is 1.5 meters per second. The total momentum after the momentum for mass 1 is -4. The momentum for mass 2 is going to be 3 because it's 2 kilograms multiplied by 1.5 meters per second. So the total momentum after is -1 kilogram meter per second, which is what we expected. It's the same before and after the collision. Okay, so you will do the same process for the next 2 setups here. The masses are slightly different, the velocities are slightly different, and you're going to observe what happens. A good thing would be to do first is make a prediction about what you think will happen when the objects collide, run the simulation, and see if it matches your prediction. So for this first part, the masses were the same, right? Both 2 kilograms. When they're moving in opposite directions, they bounce off of each other and they switch velocities, right? The first one was going at 1.5. The second one was going at -2. After the collision, they completely switched, right? So when you're dealing with like billiard balls, right? If they're moving towards each other like this, they're going to bounce off and move in the opposite direction. And it's almost like they switched velocities. Now they're going the other way, if that makes sense. Now, the other 2 examples here have different masses. So you won't see that exactly happening. But for 2 objects with the same mass, they're just going to bounce off. So that's how you're going to set up the part for elastic collisions, where they just bounce off of each other. The second part is focused on inelastic collisions. For an inelastic collisions, these are the types of collisions where the objects collide and they stick together and they move as one unit after the collision. So for example, 2 cars colliding, they get entangled with each other and they stick together, and after they collide, they kind of skid off and move as one object. Okay. Or two football players running towards each other. They collide together, they grab onto each other, they stick together, and they kind of move forward together as one unit. Those are called inelastic collisions. In inelastic collisions, the momentum is still conserved after, so it's going to be the same momentum before and after the collision, but energy is not conserved. Because in an inelastic collision, if you think about two cars colliding, what happens to the cars? They get crunched, right? There's energy loss in the crunching of the vehicle, right? It takes energy to like damage the vehicle. There's also sound and heat generated. There might even be sparks, light generated too. So that energy is not conserved. It's not like a spring where they just bounce back anymore. They collide, the energy is lost because that energy goes into the crunching of the vehicles, deforming them. Heat is generated, sound is generated. That's energy lost, right? So the kinetic energy after they collide is not the same as it was before they were colliding. Let's run the simulation for an inelastic collision where I have mass 1 and mass 2 both at 2 kilograms. And in this case, the velocity for mass 1 will be 1.5 and the velocity for mass 2 will be 0 before the collision. The momentum before they collide, let's calculate that. It's going to be mass times velocity for the first one. So that's going to be 2 times 1.5. That's going to be 3 kilogram meter per second. The second one, its mass is 2 kilograms, but it doesn't have any velocity. So it doesn't have any momentum. So the total momentum before the collision is just 3 kilogram meters per second. Let's run the simulation and collide them and determine their final velocity after and their total momentum after. So when you're doing the inelastic case, the first thing you want to do is take this little bar over here and switch it to completely inelastic. Okay, so we're going to slide this all the way to the left-hand side. Okay, the masses were both 2 kilograms. The velocity for this one was 1.5, and the velocity for the second one was 0. There's my daughter in the background. She's very much wanting to be in my video with me. All right, so the initial momentum is 3 kilogram meter per second. Let's run the simulation and see what happens. So here they collide and notice that they stick together and they move as one unit. Their velocity is 0.75. Now that's the velocity for both of them because they're stuck together as one unit, right? So they're going to have the same velocity afterward. And their momentum is 1.5 for each thing. Let's figure out the final momentum. So their velocity is 0.75. Let me go back to the lab manual. So after the collision, they were both moving at 0.75 meters per second. And after, right, they collide, they stick as one thing, right? So their momentum now is like their total mass of both of them, which is 4 kilograms. And I'm going to multiply that by their velocity after, which was 0.75 meters per second. And if I plug that into my calculator, I get 3 kilogram meter per second, which is the same as the momentum before. It was 3 kilogram meters per second before, it's 3 kilogram meters per second after. So it matches, that's what we expect. So the inelastic is a little bit different because after they collide, they stick together. So you can treat them as one mass with the total masses combined, and they have one velocity afterward because they're stuck. So check and see what happens for situations 2 and 3 here. Make a prediction about what you think should happen, and then run the simulation and see if it matches your prediction. In all cases, though, you should see that the total momentum before is equal to the total momentum after. There's a few more concept questions here that I'm asking you to work through, but most of those should not be too difficult. Overall, main idea here is to see the difference between inelastic and elastic collisions and apply conservation of momentum to both situations. Now, just a quick side note, you might be wondering, well, after two objects collide and maybe they stick together, right? The cars gradually slow down and stop, right? So the momentum is zero at the end. Right? That's because after they collide and they start to maybe skid off, there's friction acting on these two objects to gradually slow them down, right? And so their momentum will gradually go to zero. But if you just think about the momentum right before the collision and right after the collision, you can usually apply conservation of momentum because there's no external forces to slow them down or make them go faster, right? So the momentum is conserved if you consider it immediately before the collision and immediately after. Now, if it was a frictionless area, like two ice skaters colliding and moving as one unit after, you can kind of see it a little bit more clearly, right? Because there's less friction. So once they collide, they're going to move as one unit after and keep sliding off in that direction, right? So it's easier to see momentum conservation in that case. But even in the cases where there's like external forces slowing it down, if you just think about right before the collision and right after, you can apply conservation of momentum there. All right, so I hope this helps. If you need to meet with me on Zoom, if you have additional questions, feel free to reach out through email, and I'll see you soon. Bye.